Next, we'll talk about approximations of functions. In general, if you have some complicated function f of x, you are typically trying to approximate it with some simpler function, and usually a simpler function would be some polynomial of degree m, let's say Pm of x. Essentially, f of x is given by Pm of x plus some error or remainder term Rm of x. Usually we select polynomials as approximating functions because they're pretty easy to manipulate with. So let's say we can easily take the derivative of the polynomial, we can easily integrate polynomials, and so on. Usually we try to deal with the polynomials that are the simplest, such as the linear polynomials or just linear functions, or quadratic polynomials or quadratic functions, and then we'll get the approximations for our more complicated function that are linear or quadratic. So let's say if I look at some function whose plot looks like this, what is my linear approximation? So for example, if I took some point, let me call it x0, some initial point, then this is my f of x, right? A linear approximation would look like the tangent line to our function that passes through the point x0, f of x0. All right, so this is the tangent line at the point x0, and you can see that the approximation is really good around the point x0. This line almost coincides with the function, right? So, but as we move far away from the point x0, the error, say the distance between the original function and our linear approximation, becomes large. The quality of approximation gets much worse when you move away from the point x0. But in some very small proximity of x0, in some epsilon neighborhood of this point, it will be quite a good approximation. When we characterize the local properties of the function, the properties of the function around this point x0, this is good enough. Okay, so this is linear approximation. Then your quadratic approximation could be something like this. So in general, in higher dimensions, let's say in 2 dimensions, if I have some 2-dimensional region, right, and I have some point x0, then the neighborhood of this point is what we call the epsilon ball around this point. So open epsilon ball will denote it by b epsilon of x0. So this will be the set of points in Rn. So in this case, n is equal to 2, right? So we have 2-dimensional space, such that the distance between x and x0 is less than epsilon. Strictly less sign here. So the boundary is not included. That's why we call it an open epsilon ball. And then we'll have also a closed epsilon ball around x0, which is the set of points in Rn such that x minus x0 is less than or equal to epsilon. So in this case, we have less than or equal to, okay, so the boundary is included. So the points on the boundary are included in this closed epsilon ball. But now, let's continue talking about the approximation of the function. In general, I could have a higher degree polynomial approximation of our function. So, and in fact, the Taylor's theorem tells me that if my function f is, let's say, m plus 1 times continuously differentiable on some open interval, then f of x can be represented as the sum of Pm of x and Rm of x, where my Pm of x will be a polynomial of degree m, sum for k between 0 and m of kth order derivative of f in x0 divided by k factorial times x minus x0 to the power k. Okay, so this is the approximating polynomial term. K starts with 0 here. The 0 order derivative at x0 is nothing else but just f in x0. This is how it is defined. And then 0 factorial is 1 by definition. So you just have f of x0, then if I look at next term, it will be the first order derivative of f in x0 divided by 1 factorial, which is just f prime of x0 divided by 1, just f prime of x0, right? Let's discuss also this error term here. Error term is given by the expression that involves the m plus first order derivative. So it will be actually the m plus first order derivative of f in some point. Now it's not going to be x0, but it will be some point xc, which we'll discuss a little later. So divided by m plus 1 factorial multiplied by x minus x0 to the power m plus 1. So now what is this point xc here? Xc is actually a point that lies between x and x0. Alright, so you see I'm approximating this function f of x by this polynomial. Approximation will be good around point x0. And the error is expressed by this term where xc is some point between x and x0, and we don't know what exactly that point is, but the Taylor's theorem tells us that such a point between x and x0 exists. If I know that my fm plus 1 of x is less than or equal to some constant for any x in some interval ab, where the point x that I'm considering here belongs to this interval and x0 also belongs to this interval, then I can say that this error term Rm of x is actually bounded by this constant times x minus x0. Since both x and x0 belong to the interval ab, we know for sure that x minus x0 cannot be greater than b minus a divided by m plus 1 factorial. Then this will give me the bound on the error. Alright, so usually we will not really write this error term explicitly, but we will use the asymptotic notations such as big O and little o to express the error. So what are these big O and little o notations? So let's say we have f of x is equal to big O of g of x as x tends to x0 if the following is satisfied. So there exists some constant c greater than 0 and some epsilon. Greek epsilon is typically used to represent some very small positive quantity. F of x is big O of g of x if there exists a constant c and some small epsilon greater than 0, such that f of x, the absolute value of this, is asymptotically bounded by this constant multiplied by g of x for any x in the epsilon ball centered at x0. So which means that essentially the distance between x and x0 is just less than epsilon. The key idea here is that I can bound this function f of x by the function g of x, perhaps with some constant, but when we are talking about asymptotic bounds, these constants, they're not really important. So but let's say if my error is expressed in terms of some complicated function f of x, I can replace that error term with this expression here where g of x is selected to be a simpler function of x. Alright, so for example here, when we talked about the error bounds like Rm of x was given by quite a complicated expression, so which was given by fm plus 1, so the m plus first order derivative of f in x0 divided by m plus 1 factorial multiplied by x minus x0 to the power m plus 1. So instead of writing this whole thing here, I can say that this is big O of x minus x0 to the power m plus 1. Alright, And of course, in this case, we are talking about this big O relation when x tends to x0, obviously, right? So in particular, in this case, if I look at Rm of x divided by x minus x0 to the power m plus 1, then what do I get? So Rm of x is given by this expression here, and we divide it by x minus x0 to the power m plus 1. As a result, I'll just get the m plus first order derivative of f in x0. And by the way, it was not x0, it was some xi, right? So, but it's not as important in this case. The important thing is that this ratio here that we have is actually a constant, okay? So it's a constant, and therefore I can say that, for any x here, my Rm of x is less than or equal to, in fact, it is equal to, right? But in this definition, it is sufficient to say it's less than or equal to the constant given by this here. So let me denote this by c. And this is a constant with respect to x, right? So it's less than or equal to c times our function, in this case, our function g is given by x minus x0 to the power m plus 1. So now, similarly, little o notation is used to represent the errors or some other functions when we want to replace them with something simpler. So what is little o notation? We have f of x is little o of g of x for x tending to x0 if we just have the limit of f of x divided by g of x, and in fact we can take absolute values here, when x tends to x0 is 0. Okay, so essentially it tells us that we can neglect f of x compared to g of x around the point x0. For example, again, let's go back to this error term here, like Rm of x. So we already saw that this Rm of x is big O of x minus x0 to the power m plus 1. But sometimes, depending on the situation, it may be more convenient for us to say that this is O small of, say, x minus x0 to the power m. I could replace m here with any degree which is less than m plus 1. So now, why is this the case? Because if I divide Rm of x by x minus x0 to the power m, then I'll get f m plus 1 at xi divided by m plus 1 factorial multiplied by x minus x0. And of course, this tends to 0 when x tends to x0, right? So because this part here tends to 0, this is a constant, so the whole thing tends to 0. So obviously, this error here is much smaller than this function here, the polynomial of degree m around point x0. So we discussed the Taylor's theorem where we approximate f of x with a polynomial of degree m, and most often we will use quadratic approximations or linear approximations. So let's consider these two cases in more detail. So what will be a linear approximation? We'll have f of x0 plus f prime of x0 times x minus x0, and then plus we have the error term. And usually we'll write this error term as either big O of x minus x0 squared, or we'll write it as little o of x minus x0. Okay? So either way is okay. So depending on the situation, we could use one or the other. So then for the quadratic approximation, we'll have f of x is given by f of x0 plus f prime of x0 times x minus x0, and then plus 1/2 f2 prime of x0 times x minus x0 squared, and then plus O small of x minus x0 squared. or we could write big O of x minus x0 cube, same thing as here. So now this is for functions of one variable. So when we have functions or more than one variable, then we can actually write similar expressions. There is Taylor's theorem for this case as well. So this is in case when f of x is from Rn to R. And for the linear approximation, our f of x will be given by f of x0 plus, in this case, we replace f prime of x with nabla f in x0. So now it's a vector, right? And it's a column vector, so we transpose it and multiply it by x minus x0. And then plus, we could write big O, the norm of x minus x0 squared, or we could write little o of x minus x0, the norm of the difference. All right, so this is linear case. For quadratic approximation, we could use f of x is given by f of x0 plus the gradient of f in x0 transpose times x minus x0, and then plus the quadratic term will be now 1/2 x minus x0 transposed times the Hessian of f in x0 times x minus x0. All right, so and the error term could be just expressed as O small of x minus x0 squared. Okay, so these are the approximations that we'll use to develop the results that we need in order to characterize local optima for our nonlinear optimization problems. So these are very important results. So these are some approximations that are used very often. Okay, this is again the linear approximation, and this is the quadratic approximation.